Welcome back to our session on information-theoretic estimators and the JIDT software. In this short video, we're going to look at the box kernel estimator and how to use that in JIDT. So, kernel estimation looks at estimating the probability density functions using what we call a kernel function, which measures a similarity between pairs of samples. Here we're going to look at an example for two-dimensional data, and it looks at measuring their similarity using a resolution or kernel width R. So what we do for our given sample n, we average over all of the other samples, looking at taking the magnitude of the difference between point n and point n prime with respect to some resolution, and then we put that through what we call our kernel function. By default, the kernel function that we use, and the one used in JIDT, is a step or a box kernel. So we simply have a zero contribution if the difference between the points is greater than r, and here we're taking the maximum deviation in either x or y, or if it's less than r, we have a contribution of 1. And so the norm, as I said, is the maximum distance. So basically what that's doing when we're adding it up over all of our points, we're counting the number of other points that are within R at maximum of our point N. Okay, that's what we're doing with our box kernel. The values that we get may change if we make other choices for our kernel. We could have what we call a Gaussian kernel, for example. But here in JIDT, we're just using a step or a box kernel. So this computes a probability estimate, and then we can change that by dividing by our box size into our probability density estimate. Once we've got that, we can put that computation in to our entropy calculation, or really our differential entropy calculation. Here what we're doing, as you can see, we're simply averaging for all points of the log of the probability density. We can think about the change from, we can notice here the change from the definition of the differential entropy, which had an integral, to what we see in front of us. Here what we're doing, we've translated our fx dx into 1 over n. So we're averaging over all the points. So it's giving the same, essentially the same function. That's how it's doing. It's going to average the log of the probability density over all of the points. Okay, let's have a quick look at what this looks like in the space of the samples. Here, thinking about computing the mutual information between x and y. When we estimate these when we make these probability estimates, what we're really doing is measuring the probability of other points being within R. So if this is our focal point here, we're counting how many points are in this box at a maximum distance of R, and we're using that to compute the probability in the joint space, and then for counting the number of points within our x and our y slices for the marginal values here. And we use the same box width for every point. So for a point down here, we use the same box width, and we see that the probabilities are going to be very different because there's far fewer samples in these slices and in this box. So I've said before that information theory is all about questions and answers, and we need to think about our estimators in terms of the question that they're asking. So here with the box kernel estimator, the question that the mutual information is asking becomes, how does knowing x within a resolution R help me to predict y within the same resolution R? Okay, it's important to bear in mind different estimators are answering the question about mutual information in a slightly different way. We also need to consider how to choose the resolution R. I'm not going to go into that here. I will refer you to the paper introducing the toolkit, in particular to the appendix marked here, to talk about some heuristics for doing so. We also need to bear in mind the pros and cons of our estimation technique. Here, the pro for box kernel estimation, in comparison to the Gaussian estimator we already looked at, is that it's model free. So now it can capture non-linearities, which the linear Gaussian estimator could not. That's important. On the downside though, the cons are that it's very sensitive to R. Okay, so we have some heuristics on how to choose R, but it's still sensitive to that. It's also quite biased. It's very biased, and it's much less time efficient than the linear Gaussian estimator was, although that can be reduced with good neighbor search techniques. Let's have a look at how to run it. All we need to do is select kernel from the estimator type drop-down box, and then we can see which parameters we have available. The most crucial one is the kernel width, R. And look at that, I've misspelled that. That's nice, isn't it? So that's the most critical one. Okay, the others you can read about in the pop-ups in the GUI and so on. Let's have a quick look at that. So here we'll change our calculator type now to kernel. We'll leave the same data file and the same, we'll look at source column 0 to destination column 1. We'll also look at doing a time lag of 1, so we pick up where we know the relationship is. As I say, the kernel width is the key parameter here. There are other parameters that we can look at too. For example, whether we normalize the data beforehand or not. I recommend you do that. The default value is true. Okay, and we can see that for true false values, we have a drop down. We don't have to type the whole value in. Okay, let's compute that for a kernel width of 0.25. Okay, now our answer is in bits. Comparing this to what we got before with the linear Gaussian estimator, which was reasonably good because we know the data is Gaussian with a linear relationship. We get a much larger value here, 1.05 bits compared to 0.37 nats before. This is most likely because we've got a very small amount of data and a significant bias in what we're computing. We also know it's very sensitive to the kernel width. If I come in here and change this to 0.5, we're going to see a very different value coming out there. So that shows just how sensitive this estimator is. Okay, that's all I want to show you about the kernel estimator. It's not my first choice estimator for continuous value data. The best of breed, really, if you want to go fully nonlinear, is the Kraskov or the KSG estimator, which I'm going to show you in our next short video. So I'm not going to say anything more about the kernel estimator. I just wanted to show it to you first, because it's important we understand that first so we understand why the KSG estimator works the way it does. And we'll have a look at that in our next short video.